Okay, let's unpack this. Welcome to the deep dive. Today, we're really getting into the nitty-gritty, tackling what feels like the Mount Everest of enterprise IT, moving all that complex on-premises stuff, the VMs, databases, legacy apps, Active Directory over to AWS, and doing it efficiently, securely. We've got this massive toolkit, basically 51 different real-world migration scenarios to guide us. This isn't theory, it's the practical playbook. Our mission here is to pull out the absolute must-knows, the biggest gotchas, the dependency traps, and those critical strategies for getting near zero downtime. We want to give you a clear roadmap you can actually use.
What's fascinating here is, well, everyone knows why they want to move to the cloud, right? But the how, that's where it gets complicated. People often underestimate the sheer tactical difficulty. Like these scenarios show, it's just not a simple lift and shift. It's more like a high-stakes orchestration puzzle. The real value of digging into this source material is finding those tiny details that prevent disaster. Things like, accidentally breaking file permissions or losing session state for your critical apps. It demands precision.
Right, precision.
So to make sense of all this detail, we're going to take it chronologically, like a real migration. We'll start with the absolute basics, assessment, planning. Then we'll move into the core workloads like databases and file systems where downtime is just not an option.
Yeah, the really sensitive stuff.
Exactly. Then we hit the high-risk infrastructure, Active Directory being the prime example. After that, techniques for near-zero cutover, and finally wrapping up with optimization and how to gracefully switch off the old on-prem gear.
Okay, let's start right at the beginning then. You mentioned the biggest risk is not knowing what you've got. So if you're staring at hundreds of Hyper-V and VMware VMs, what's the absolute non-negotiable first thing you do before any data moves? Hashtag tag 1.1, the end-to-end migration blueprint, scenario one.
Discovery and assessment. Absolutely foundational. Success really hinges on getting this right. You need to inventory every single VM, and not just the name. You need detailed performance metrics, CPU, memory, I/O, network throughput, and crucially, collect this over time, not just a snapshot.
Why over time? Is it just about averages?
It's about peaks and troughs. It tells you what the real demand is. This data is critical for right-sizing later in AWS. If you just move a VM based on its on-prem specs, say 16 cores, you'll likely overspend in the cloud. Or worse, you might even hit performance issues because cloud resource allocation works differently. So metrics first.
Okay, so we know what we're moving. We've got the metrics. Now, how do we actually move it? What's the go-to tool suggested here for rehosting those VMware or Hyper-V VMs?
For rehosting, basically lifting the OS and apps as they are, the recommendation is AWS Application Migration Service, MGN for short. MGN is really designed to simplify and speed up these big migrations. It automates a lot of the conversion and the cutover process.
But before you even run MGM.
Right, you need the landing zone. That's your foundation in AWS. The staging area, replication servers, and absolutely critical, the network setup. Your VPCs, subnets, security groups, and that connection back home VPN or direct connect. That has to be solid first.
Okay, landing zone's ready. How does MGN actually cut down the downtime? I mean, if copying a server takes hours, you can't afford that outage.
That's the clever part. You install a small AWS replication agent on the source VM, Windows or Linux, doesn't matter. This agent starts a continuous block-level replication to that AWS staging area. This is huge. It copies everything block by block OS, apps, config, and keeps the AWS copy super up to date. We're talking minutes, sometimes seconds behind the source.
Ah, so the big copy happens while the source is still live.
Exactly. The final cutover then becomes really quick. You just pause, writes on the source briefly, sync the tiny final difference, launch the EC2 instance in AWS, and flick the DNS switch. And crucially, while all this replication is happening in the background, you do non-disruptive test launches in AWS. Test everything without touching production.
Hashtag tag 1.2, automating discovery and dependency mapping.
Okay, continuous replication helps, but with hundreds of VMs manually tracking how they all talk to each other, that sounds like a recipe for disaster. Dependencies are key.
Absolutely impossible manually. The risk of human error is just too high. You need automation for that mapping.
Which brings us to scenario 51, mentioning AWS Transform. How does that fit in with MGN?
Think of MGN as the engine doing the moving, and AWS Transform as the planning brain. Transform is built for that large-scale complexity. It automates discovery, maps out those dependencies in detail by watching network traffic, helps with network planning, and really importantly, helps you plan the migration in logical waves.
Waves, you mean grouping-related servers? Precisely. Applications often have tiers. Web servers talk to app servers talk to databases. Databases might need a file share. Transform helps you see that. It stops you making that classic error of moving the web front end before the database it relies on is ready in AWS. If you've got a complex setup, skipping transform is just asking for trouble. Hashtag 1.3 addressing regulatory constraints and licensing, scenarios 9 and 8.
Right, planning is key. But what about the non-technical roadblocks? Compliance, cost. Scenario 9 talks about regulatory constraints, specifically data residency. Data can't leave certain countries. How do you manage that?
Yeah, that requires real discipline, geographical discipline. It starts obviously with picking AWS regions that are physically within the allowed jurisdiction.
Okay, seems straightforward enough.
But the trap is the secondary services. You have to make absolutely sure that everything associated stays local too. Backups, disaster recovery, even logs. They all need to stay within those permitted borders. It means using local encryption keys, being careful with key management, and definitely avoiding any AWS service that might replicate data globally, even if it's just metadata. You need meticulous documentation of data flow. A slip-up here is an instant compliance failure.
Ouch. Okay, compliance covered. What about cost, specifically licensing? Scenario 8, Windows and SQL Server licenses with software assurance, SA. What are the options?
SA gives you flexibility. The most common route, often the cheapest, is BYOL, bring your own license. Microsoft License Mobility rights let you apply existing licenses to certain AWS setups, like dedicated hosts or specific instance types.
And that saves money compared to paying AWS for the license.
Usually, yes, significantly over the pay-as-you-go, license included AMIs. But BOWL has rules. Specific instance types might be required. If you don't have SA or your licenses don't qualify for mobility, then you have to use the license-included AMIs, where AWS bundles the license cost into the hourly price.
So you need to check your agreements carefully.
Absolutely. And the critical thing highlighted here is the need for audits, before and after migration. You must prove you're compliant with Microsoft's terms. It often involves detailed core counting and making sure your chosen AWS instances are eligible. Get it wrong, and you face penalties. Hashtag 1.4, the inevitability of the undocumented scenario 32.
Okay, we've planned, we've assessed using Transform, replication's running, but let's be real, legacy IT is never perfectly documented. Scenario 32 tackles that moment of horror.
Yeah.
You find an undocumented dependency mid-migration.
Yeah, the hidden script, the forgotten file shared, some ancient certificate server no one knew was still active. It happens.
What do you do? Push through, hope for the best.
No, absolutely not. The immediate disciplined response, and it goes against every instinct when you're on a deadline, is pause the migration wave. Right there.
Pause. But delays cost money. Project managers get nervous.
I know. But the cost of a short pause is nothing compared to the potential cost of instability, data corruption, or application failure hitting you later, maybe weeks later, when it's much harder to diagnose. If you rush past it, you're injecting a total unknown into what should be a controlled process. You have to stop, surface the dependency, document it properly, add it to the migration plan, maybe adjust the sequence, and then retest everything connected to it.
So pausing turns a potential crisis into just a managed engineering change.
Exactly. It saves so much pain down the line.
Yeah.
So if the VM is the body, the database, and the file system, they're the heart and lungs. They just can't tolerate downtime, which means we need specialized strategies here. Continuous synchronization is key, not just the basic rehosting we use for simpler servers. Hashtag 2.1 database migration paths and tooling. Scenarios 2, 11, 23.
Okay, let's start with SQL Server, Scenario 2. Lots of organizations want to move from SQL on VMware to a managed service like Amazon RDS. But how do you know if your database is even compatible? And how do you move it with minimal downtime?
Good questions. The first step is that compatibility check. Does your SQL Server use features RDS doesn't support? Things like complex cross-database queries, maybe custom CLR code, or very specific SQL agent job configurations. If it's mostly standard stuff, then moving to RDS is usually the best strategic move. You offload all that patching, backup management, HA. It's a huge operational win.
Makes sense. And the tool for that minimal downtime, move to RDS.
That's AWS Database Migration Service, DMS, built for this. DMS handles the initial schema conversion, loads the data, and then this is the crucial part. It switches to continuous replication. It captures transactions from the source and applies them to the RDS target in near real time. So the bulk of the data moves while you're live. The only downtime is for the final quick sync and DNS cutover.
Okay, but what if that compatibility check fails? What if the database needs those features RDS doesn't have?
Then you're looking at running SQL in EC2. Basically, you treat it like a specialized server. You'd likely use AWS MGN to lift and shift the VM itself. But, and this is important, you still need database-aware synchronization for the final cutover. MGN's block-level sync is great, but it doesn't understand transaction consistency like native SQL tools do. So you might use SQL's own log shipping or replication for that final tiny cutover window.
Got it. And does this apply to other databases too, like Oracle or open source ones? Scenarios 11 and 23 touch on this.
Yes, the principle is similar. For Oracle, MySQL, PostgreSQL, as in scenario 11, AWS DMS is still often the primary tool. Or you can use the database's native replication features. The process is the same. Full load first, then continuous change, data capture, CDC, or transaction replication.
And for the really huge ones, Scenario 23 mentions large Oracle DBs.
Right. For those massive multi-terabyte databases where the business impact of even an hour's downtime is unthinkable, you often lean on more specialized, sometimes proprietary tools. Think Oracle DataGuard or Golden Gate. These are engineered for high-volume, near-synchronous replication over distance. They aimed to get that final cutover window down to just minutes. Hashtag tag 2 chag 2.2 migrating complex file servers and ACLs, scenarios 4, 18, 13.
Okay, database is handled. Now, file servers, they seem simpler, but Scenario 4 warns about preserving terabytes of data and those complex NTFS permissions, the ACLs. Mess up the ACLs and your security is shot.
Exactly. File servers are deceptively tricky. You absolutely need to preserve those ACLs. So the target service in AWS has to understand them natively.
Which means
Usually AWS FSX for Windows File Server, or maybe FSX for NetApp ONTAP if you have specific needs like multi-protocol access. These services integrate with your VPC, join your Active Directory, and handle SMB and NTFS permissions, just like an on-prem server.
Okay, target identified. How do we actually copy the data and crucially those permissions? Scenario 18 must cover this.
Yes. Tool selection is non-negotiable here. You need something that explicitly preserves metadata, especially ACLs. The classic tool is Robocopy, the Windows utility, but you have to use the right flags.
What flags are those?
You need copyl or at least copy.datso. That tells it to copy data, attributes, timestamp security, the ACLs, and owner info. Miss the S for security, and you've just moved files with no access control. Big problem.
Sounds prone to error. Is there a better way?
For larger scales, definitely.
Yeah.
AWS Data Sync is the preferred tool. It's designed for large transfers over the network and is built to preserve all that metadata, including ACLs, automatically. Much less risky than getting robocopy flags wrong.
Right, and minimizing downtime for these active file shares. People are saving documents all the time. Scenario 13 must have a strategy.
It's a staged approach using continuous sync. First, inventory the shares and permissions. Second, use data sync to precede the bulk of the data, maybe overnight or over the weekend. Get 99% across. Third, run data sync continuously or at least frequently to pick up the ongoing changes, the delta.
And the cutover itself.
Strict protocol. You need a brief change freeze. Stop users writing to the source share. Verify data sync has got the very last changes. Then quickly update your DNS names or DFS namespaces to point clients to the new FSX file server. The outage is just that redirection time.
Okay, this is where it gets really interesting, maybe a bit scary. The high-stakes orchestration puzzle, as you called it. Get the sequence wrong, move the wrong thing first, and boom, everything breaks. Hashtag tag 3.1 orchestration and sequencing, scenario 5.
Exactly. This is where that dependency mapping from tools like AWS Transform becomes absolutely critical. Scenario 5 lays down the rule. Understand the order. The foundation has to be stable in the cloud first. That means your database tier, your shared storage like FSX, those things must be migrated and running, or at least fully replicated and ready to cut over before you move the applications that depend on them.
Makes sense. So back end first. Once that's solid in AWS, how do you handle the front end, say the web servers, without causing a big user-facing outage?
For those tiers, especially if they're stateless, you use techniques designed for safety and rollback. Think blue-green deployments or maybe a canary release. You stand up the new web servers in AWS, that's your green environment. Point them at the already migrated database and file shares in AWS. Test them thoroughly internally.
And then you switch the traffic.
Gradually, use a load balancer, like an AWS application load balancer, or carefully manage DNS weighting to start sending a small percentage of real user traffic to the new green environment.
Ah, so you can watch it live.
Exactly. Monitor closely. If everything looks good, you ramp up the traffic to green. If you hit any unexpected snags, you can instantly switch all the traffic back to the old blue on-prem environment. Low risk, quick rollback. Hashtag tag 3.2 migrating Active Directory domain controllers. Scenario 3.
Okay, sequencing makes sense. Now for arguably the most critical piece, Active Directory. Scenario 3 gives a stark warning. Do not just lift and shift your existing domain controller VMs. Why is that so dangerous?
Yeah, that's probably the single most important don't in the whole migration playbook. You absolutely positively do not use MGN or any VM cloning or migration tool on an existing domain controller.
Why not? What breaks?
It's deep in how AD works. AD relies on things like machine IDs, replication metadata, even network specifics. Moving an existing DC VM can cause USN rollbacks, replication failures, conflicts with its own identity. Essentially, you risk corrupting your entire AD forest. It's incredibly fragile.
Yikes. Okay, so if we can't move the existing ones, how do we get AD into AWS?
You extend the domain, you don't move it. The strategy's clear. 1. Build new. Launch a fresh, clean EC2 instance in AWS using the same Windows version as your current DCs.
Okay.
2. Join. Join it to your existing on-prem AD domain just like any other member server. 3. Promote. Then promote that EC2 instance to become an additional domain controller. Let it fully replicate SYSVL and the AD database from your on-prem DCs. This takes time. Let it stabilize. 4. Roles. Carefully. Only once replication is proven healthy and stable for a good while should you even consider transferring the FSMO roles, those critical master roles, to the AWS DC. 5. Configure sites in DNS. Update your AD sites and services to define the AWS network segments correctly. And crucially, make sure clients migrating to AWS start using these new AWS DCs for their DNS resolution.
So you end up with DCs running both on-prem and in AWS, replicating between them.
Exactly. It's a robust, resilient hybrid setup during the migration. Then, as you decommission on-prem servers, you eventually decommission the on-prem DCs last. Much, much safer. Hashtag tag 3.3, addressing hard-coded IPs and DNS resolution. Scenarios 2036, right? Another hidden migration killer. Hard-coded IP addresses. Scenario 20 flags this. So many older apps, scripts, config files point directly to an IP. Move that server, it gets a new IP in AWS.
And the application breaks instantly.
Instantly. The best fix is architectural, really. Push developers and sysadmins to always use DNS names, never IPs. Then, during migration, you just update the DNS record, maybe a CNAME or an alias record in Route 53, to point the existing name to the new AWS IP address, transparent to the application.
But what if you just can't change the app? Some ancient thing.
Yeah, that's tough. You might need temporary network address translation at tricks, or maybe keep the old IP address using specific AWS networking features, but that adds complexity and potential bottlenecks. DNS is always cleaner if you can manage it.
And in that hybrid phase with stuff on-prem and stuff in AWS, how do we make sure everything can find everything else via DNS? Scenario 36 mentions coexistence.
You need seamless name resolution across both environments. The standard way is conditional forwarding. You configure your AWS DNS resolvers, maybe Route 53 resolver, or your new ADDCs in AWS to say, if you get a request for mycompany.local, your on-prem domain, forward it to the on-prem DNS servers.
And vice versa.
Exactly. Your on-prem DNS servers need a conditional forwarder saying, if you get a request for aus.private.zone or whatever your AWS private zone is, forward it to the AWS DNS resolvers. That way, lookups work no matter where the client or the server actually sits. Hashtag tag 3.4 handling complex configuration requirements, scenarios 43, 34, 42.
Okay, infrastructure's looking better. But what about the specific fiddly configurations on servers, like Windows ISO web server, scenario 43? MGN moves the VM, but does it get all the ISA settings right?
Not necessarily. MGN moves the disk blocks. It doesn't inherently understand ISA application pools, bindings, or custom modules. You absolutely need to handle ISA config separately. The process involves backing up the ISA configuration before migration. You can use the appcmd tool or just grab the XML config files. This captures your site definitions, app pools, port bindings, any special modules you've installed.
And SSL certificates.
Crucially, yes, back those up too with their private keys. Then, after the VM is migrated and running as an EC2 instance, you import that backed up ISA configuration, make sure any custom DLLs or modules are present and registered, and then meticulously rebind the correct SSL certificates to the site bindings. Miss a step, and you get site errors.
Sounds detailed. What about Linux? Scenario 34 talks about ensuring consistency, especially things like cron jobs or specific, etc. file changes.
Yeah, consistency is key, especially if you have a fleet of Linux servers. You can't rely on manual changes post-migration. Automation is your friend here. You need to capture the critical configuration state user accounts, critical files, and etc., sudoers, permissions, cron jobs, maybe system unit files, and have a way to reapply it reliably on the new EC2 instances.
Tools like?
This is perfect territory for configuration management tools. Ansible, Chef, Puppet, SaltStack, even well-managed shell scripts. The goal is to make the target EC2 instance configuration identical and repeatable, preventing configuration drift.
Okay, and one last tricky one. Scenario 42, Kerberos authentication failing for 80 joined Linux machines after migration. What's the usual suspect?
9 times out of 10, maybe more, it's time sync. Kerberos is incredibly sensitive to time differences between the client and the domain controller. Even a few minute skew can break authentication.
So check NTP first.
Absolutely. Make sure the Linux box is syncing time correctly, ideally with the AWS DCs or a reliable source. If time is okay, then check DNS again. Can it actually find and reach the new AWS DCs? And finally, dig into the Kerberos 8 join configuration itself. Is ISDSD or Realm configured correctly for the AWS environment? Are the Kerberos key tab files valid? Are the service principal names, SPNs, registered correctly in AD for the new server context? Usually it's time, DNS, or config. Tag 3.5 network mapping and legacy components, scenarios 15, 6, 14. We also see complexity in networking beyond just DNS, scenario 15, for instance. Servers with multiple network cards on-prem, maybe one for management, one for application data, one for storage traffic.
Yeah.
How do you replicate that in AWS?
Right, an EC2 instance usually just has one network interface by default.
You need to use multiple elastic network interfaces, or ENIs. You can attach several ENIs to a single EC2 instance. Each ENI can have its own private IP address and be placed in a different subnet within your VPC. So you map the on-prem management NIC traffic to an ENI in your management subnet, the data NIC traffic to an ENI in your data subnet, and so on. You then use security groups attached to each ENI to control the traffic flow precisely, replicating that on-prem network segmentation.
Okay, multiple ENIs for multiple paths. Now for some really legacy stuff. Scenario 6. A Linux VM needs a custom kernel module, maybe for specific hardware it used to talk to. AWS standard AMIs won't have that.
Yeah, this is a tough one. First, you challenge hard. Is that module really needed in the cloud? Can the function be replaced? If it's absolutely non-negotiable, you might be looking at compiling that module yourself against the kernel headers for the specific Amazon Linux or other distro version you're using and building a custom AMI. That's complex and adds maintenance overhead.
What's the alternative?
Sometimes, the path of least resistance, if the module is deeply tied to how the app works, is to treat that EC2 instance almost like a physical server. Configure it as closely as possible to the original environment, maybe even needing a specific instance type. It deviates from standard cloud practices, but might be necessary for that legacy piece.
And speaking of legacy, Scenario 14 mentions unsupported runtimes. That critical app stuck on, say, .NET 2.0 or an ancient Java version. What do you do when you can't refactor before the migration deadline?
You've got a few options, kind of a hierarchy of preference. 1. Least preferred. Run it on a Windows EC2 instance that still supports the legacy runtime. You take on the burden of maintaining that older OS environment. 2. Better. Try to containerize it. Package the old runtime and the application into a Docker container. This isolates its dependencies and makes it easier to manage on a modern host OS. 3. Best, long-term. Use the rehosting migration as step 1. Get it running on EC2, but immediately put it on the roadmap for proper modernization or stepwise refactoring to a supported version or a cloud-native architecture. Don't let it sit there unchanged forever.
Right, we keep coming back to downtime. It's the currency of risk, isn't it? For anything critical, the goal has to be near zero cutover. That often needs more advanced synchronization than basic replication. Hashtag tag 4.1, achieving near zero cutover, scenarios 2944.
Scenario 29 specifically asks about the techniques to get that downtime from potential hours down to just minutes. What's in the toolkit? It's really a combination approach, layered techniques. You start with that continuous replication, MGN for VMs, DMS for databases, handling the bulk data sync efficiently. Then, for the cutover itself, you need that rapid final delta sync. Sometimes, you might even implement dual writes for a short period, where the application writes to both the old source and the new AWS target simultaneously, though that adds complexity. And all of this gets orchestrated within that blue-green deployment framework we talked about. The load balancer or DNS change becomes the final, very brief switchover point.
But even a quick DNS switch can feel long if DNS propagation is slow, right?
Right.
Scenario 44 worries about that delay, clients hitting the old server long after you've cut over.
Yeah, DNS caching can bite you. The standard mitigation is to dramatically lower the time to live TTL value on the relevant DNS records well before the cutover window, maybe days or even a week before.
How low?
Really low, like 60 seconds, maybe even 30 seconds. This forces clients and intermediate DNS servers around the world to recheck the record very frequently. So when you do make the final IP address change, it propagates much, much faster. You often combine low TTLs with weighted routing in Route 53 or gradual traffic shifting via the load balancer. Start sending 1% of traffic, then 10%, then 50%. It smooths out the transition and minimizes the impact if there is a small DNS lag somewhere. Hashtag 4.2, handling high IOPS and large volumes. Scenario 730.
Okay, let's talk performance underload. Migrating high-performance databases, things hammering the disk I/O. Scenario 7 says we need the right AWS storage design.
Absolutely. If you've got workloads needing guaranteed high input-output operations per second, think database transaction logs, high traffic indexing, you can't just use standard general-purpose storage. You need to provision IOPS, PIOPS, EBS volumes, specifically IO1 or the newer IOP, IO2 block express types, or maybe the latest GP3 general-purpose volumes, but configured specifically with high IOPS and throughput settings.
And just picking the volume type is enough.
Not always. A key design pattern is separation. Put your database data files on one set of volumes, the transaction logs on a separate high-performance PIOPS volume, and maybe Tempty on another. Avoids I/O contention. Sometimes you'd even stripe multiple volumes together for maximum throughput.
And you have to test this after migration.
Mandatory. Use proper disk benchmarking tools, FIO on Linux, maybe DiskNet on Windows, run realistic load tests, and compare the results against the performance baseline you captured way back in the assessment phase. You need to prove it meets or exceeds the on-prem performance.
Okay, that's IOPS. What about just sheer size? Scenario 30, servers with huge volumes, many terabytes. The initial replication sync could take days over a standard internet connection.
Yeah, the initial sync time for massive volumes is a major hurdle. You need strategies to bypass the slow WAN link for that bulk data. One common approach is physical seeding. Use an AWS Snowball device, basically a ruggedized high-capacity storage appliance. You copy the terabytes onto it locally, ship it to AWS, and they ingest it directly into S3 or EBS. That handles the initial 99%.
And then the agent takes over.
Exactly. Once the data is seeded in AWS, the replication agent, MGN or data sync, only needs to sync the changes that occurred since the Snowball copy was taken. Much faster. Alternatively, if you have AWS Direct Connect with significant bandwidth, you might just let the initial sync run over that dedicated connection. But seeding is often faster for truly huge data sets. Hashtag 4.3HA and cluster migration, scenario 3112. We also need to consider systems designed for high availability on-prem, like Windows failover clusters or SQL Server always-on availability groups. Scenario 31 deals with migrating these without breaking the cluster.
Right, you can't just shut down the whole cluster at once.
No, you migrate it node by node, carefully managing the cluster quorum throughout the process. You typically migrate one node to an EC2 instance in one AWS availability zone, AZ, let it rejoin the cluster, validate health, then migrate the next node to a different AZ. Using multiple AZs is key to achieving high availability in AWS. Once all nodes are migrated, you reconfigure the cluster's networking, like the listener IP, for the AWS environment, and thoroughly test failover between the AZs.
Okay, that handles cluster backends. What about web apps and sessions? Scenario 12 revisits that common problem. Apps storing user session state locally, maybe in memory or on the web server's disk. That breaks horribly with cloud auto-scaling, right?
Breaks instantly. If you scale out, adding new instances, or if an instance fails and is replaced, any users whose sessions were on the old terminated instance just lose everything, their login, their shopping cart, whatever they were doing. The application isn't stateless.
So how do you fix that dependency on local state?
The proper cloud-native way is to externalize the session state. Move it off the web server instance entirely and into a shared, fast, highly available caching service. The prime candidate in AWS is Amazon Elasticache, using either Redis or Memcached. All web instances then read and write session data to this central cache. User sessions persist regardless of which web server instance happens to handle their request.
Could you use sticky sessions on the load balancer instead?
You can, where the load balancer tries to send a user back to the same instance every time. But it's generally discouraged. It hinders scaling effectiveness, makes deployments harder, and doesn't handle instance failure. Gracefully, the session is still lost if that specific instance dies. Moving state to Elasticache is the much more robust and scalable solution.
Okay, we've done it. The migration was successful, systems are up and running in AWS. But the job's not over, is it? And now we need to optimize, secure it properly, and actually see what's going on. Hashtag 5.1, Security and Network Policy Translation, scenarios 1937.
Absolutely. Security first. Scenario 19 is clear. You must translate your on-prem firewall rules and ACLs into the AWS equivalents, primarily VPC security groups, and maybe network ACLs and ACLs. And the guiding principle has to be least privilege. Don't just replicate old, potentially overly permissive rules. Review every rule. Only open the specific ports and protocols needed between specific resources. Lock it down tightly.
And beyond network rules.
Basic hygiene. Encrypt EBS volumes at rest. Always use KMS for key management. Use IAM roles for EC2 instances instead of access keys where possible. Enforce multi-factor authentication, MFA, everywhere you can. And turn on the AWS security monitoring services. Security Hub for posture management, Guard Duty for threat detection, Inspector for vulnerability scanning. Get that visibility from day one.
What if simple security groups aren't enough? Scenario 37 talks about translating more complex enterprise firewall policies.
Right. If you need things like intrusion prevention, deep packet inspection, or centralized filtering across many VPCs, you'll likely use AWS Network Firewall. You deploy it centrally, often integrated with AWS Transit Gateway, and route traffic through it. The process involves carefully translating your existing rule sets into the network firewall policy language. It requires rigorous testing afterwards to make sure you haven't broken legitimate traffic flows while still enforcing the required security controls. Hashtag 5.2 cost management and performance tuning, scenarios 3845.
Security is paramount. But then comes the bill. Scenario 38, the dreaded cost shock. Migration success, but the first AWS bill is way higher than expected. How do we stop that?
Visibility and proactive management again. You have to enable cost monitoring tools immediately. AWS Cost Explorer set up AWS budgets with alerts. You need to see where the money is going. Often the big culprits are easy to spot once you look. EC2 instances sized based on generous on-prem hardware that are now mostly idle. Unattached EBS volume still racking up charges, unexpected data transfer costs, dev test environments left running 247.
So what are the immediate fixes suggested?
First, right-sizing. Use those performance metrics you gathered. Scale down those oversized VMs aggressively. Use the smallest instance type that meets the actual performance need. Second, financial instruments. If you have predictable workloads, commit to AWS savings plans or reserved instances for significant discounts over on-demand pricing. Third, optimize data transfer. Use AWS services within the same region where possible, maybe use CloudFront for caching, and enforce strict shutdown policies for non-production environments. Turn them off when nobody's using them.
Okay, that's cost reduction. What about the opposite problem? Scenario 45, the migrated VM is running slower in AWS than it did on-prem.
Yeah, that usually points to picking the wrong instance type or size. First thing to check is CPU steal in CloudWatch metrics. If it's high, the underlying hypervisor is contending for resources, meaning your instance is too small or on an oversubscribed host.
The fix being?
Change the instance type. Move to one with a better, more guaranteed CPU allocation. Maybe a different instance family with enhanced networking if network performance is the issue. For really latency-sensitive applications talk to each other, consider using placement groups. This tells AWS to physically locate those EC2 instances close together in the data center, minimizing network latency between them. Hashtag 5.3 visibility, monitoring, and automation. Scenarios 2446. Cost and performance rely heavily on visibility. Scenario 24 warns about losing that monitoring capability post-migration. You can't manage what you can't see.
So standard CloudWatch isn't enough.
The basic EC2 metrics are a start, but you need more. You must install the CloudWatch agent on every migrated server. This lets you collect detailed OS-level metrics, memory usage, disk space, custom metrics, and critically, stream application and system logs to CloudWatch logs. Then you build CloudWatch dashboards that replicate or improve upon your on-prem monitoring views. Set up CloudWatch alarms based on your established performance baselines. And for applications, consider deeper tracing with AWS X-Ray or Application Insights to see inside the request flows.
Looking back at the whole process, Scenario 46 really pushes for automation using infrastructure as code, IAC. How far should that automation go?
Ideally, everything that could be automated should be. Use tools like CloudFormation or Terraform. This isn't just about the core infrastructure, VPCs, subnet security groups, IAM roles. It should also automate the migration tooling setup, like MGN configurations, the instance launch settings, and crucially, include those post-launch configuration scripts. The scripts that automatically run after an instance boost to join the domain, install the CloudWatch agent, configure IS or Apache, apply security settings. Basically, everything needed to make the instance production ready without manual intervention.
So IAC makes future migrations faster and less error-prone.
Dramatically. It ensures consistency, reduces manual effort, and makes your entire migration process repeatable and auditable.
We're almost there. Migration done, systems optimized. But the old data center is still sitting there. Scenario 33 talks about managing that hybrid coexistence phase. How long does that last?
It lasts as long as necessary and requires careful management. You absolutely must keep that stable network link, VPN Direct Connect, active. Active directory replication between on-prem and AWS must remain healthy. You also need to run your on-prem and cloud backup systems in parallel for a period, until you've performed multiple successful validated restores purely from the cloud backups. You need absolute confidence before cutting the cord. This phase could be weeks or even months, depending on complexity and risk tolerance. Finally, scenario 50, the actual decommissioning, shutting down the old hardware. What are the final checks?
You can't just pull the plugs.
Definitely not. It's a checklist process.
Ooh.
Final dependency check. Are you absolutely certain nothing anywhere still relies on these servers or storage? Archives all necessary historical logs and audit data for compliance. Remove any remaining migration agents. Then you schedule the physical power down of hosts, SANs, network gear, and critically update your asset management system, your CMDB, to formally record that these resources are gone. Don't leave ghost assets in your inventory. #shag outro.
Wow, okay. So pulling it all together, this deep dive really shows migration isn't just moving bits. It's fundamentally about that upfront assessment, picking the right tools like MGN, DMS, DataSync for the job, understanding and sequencing dependencies meticulously, and really prioritizing that near zero downtime using continuous replication and careful cutover strategies. We definitely hit on some key practical solutions for the tricky parts, like how to handle Active Directory properly extending, not lifting and managing those awkward legacy runtimes.
Exactly. And if we zoom out slightly, connecting to scenario 35, remember that this rehosting, this lift and shift we've mostly discussed, is often just step one. The real long-term value frequently comes from replatforming. That means eventually moving those databases from SQL on EC2 to managed RDS, or replacing old batch processing scripts with modern serverless approaches like Lambda and step functions. It's often a gradual process, using that strangler fig pattern to slowly replace old components with cloud-native services.
A continuous improvement journey.
Precisely. Which leads to a final thought for you, our listeners, to mull over. We talked about cost optimization being critical, scenario 38. And we talked about the careful decommissioning process needing absolute certainty, scenario 50. So here's the dilemma. Given that